All right, so today we're going to be chatting about the squeeze theorem. It's a very easy theorem. I don't like to do it right off the bat because it's almost so easy that it freaks people out, if that makes sense. Okay, so here's the deal. Suppose you have some weird oddball function. Okay, let me see if I can find one up here for you real quick. Here's a perfectly good example. Suppose I want to find the limit of, as x approaches 0, of x times sine of 1 over x. Suppose I want to find that. Okay, well, the first thing that occurs to me is obviously it does not exist at 0. We got a problem. Okay, clearly that's going to be an issue. And clearly you're right, it's going to oscillate like crazy. But does it oscillate predictably towards a value? And that I don't know. So we look at the graph and we zoom in on a little bit. And what we realize is, gosh darn, that looks vaguely familiar, bro. That looks vaguely familiar. In fact, what it looks a lot like x. Oh, wait a minute. I feel like it looks a lot like absolute value of x, doesn't it? Oh, it does, Groom. But what you'll find is that purple line is greater than, so the absolute value of x is strictly greater than this guy. Well, let me write down here. Let me backtrack. So what I notice right off the bat is I see a function I vaguely recognize, and it's absolute value x. And he's greater than or equal to it everywhere. And at no point is this guy is always less than it. Sometimes it's equal to, but it's always less than it. Now you look on the bottom side, it looks like this guy. Boom. And you're like, whoa. That means the green one is always between the other ones. It's, well, or equal to. Here's my question. Whatever thou doest to one side, thou must also doest to the other side, yes? So if I take the limit of this side, I must take the limit here. And I must take the limit here. And guess what? Nothing changes. But Groom, the limit of the absolute value of x is 0. This I do not know. But this I do know. Wait a minute. That says this limit must be what? It must be 0. Hence, we've squeezed the function. And that's all there is. And so the function, the theorem is this guy. Let me write it down for you. It says assume that x does not equal c, assuming for x does not equal c, in some open interval, that is, let's say from -2 to 2 or something along these lines, right? Oh, an open interval. Doesn't matter, but something like that. But listen, containing c. Oops, containing c. So in other words, if you're talking about 0, -2 to 2 contains 0. If you're talking about 10, -8 or 8 to 10, 8 to 12 includes 10, right? So you must include, in whatever interval you're using, not that one per se, but in any open interval, must include the limit that we're interested in, the point we're interested in, which obviously a lot of times is 0. Then for L of x is less than or equal to f of x is less than or equal to h of x on the interval. Right? Nice. Make sense? And the limit of L of x as x approaches c is equal to the limit as h of x as it approaches c. As long as those guys are equal, yay. And by the way, and exists. In other words, that's a big deal too. The limit has to also exist. Then the limit as x approaches c of f of x exists, the limit exists, and the limit is L. In other words, it's the same limit. It has to be. Okay, so we'll do a couple of examples here. Once you get going on, they're pretty much the same thing. They're kind of boring almost. Not about boring. They're just not that exciting anymore. This one here, the limit as x approaches 0 of tan x cosine of the sine of 1 over x. What the heck, Groom? What does it look like? I don't know. Oh my goodness. Groom is going to die. No, don't die, Groom. Tan x cosine of the sine of 1 over x. Oh, that's hot. Oh, look at that guy. Oh, friend. What does it look like? Groom, it looks like a couple of freaking lines. In fact, one of the lines looks an awful lot like, hear me out on this, x. Now, here's the problem with that. Here's a slight bit of a problem there, right? And then, of course, you have negative, or so, like, I don't know, what was it the other one? The other one, like 2x? Nope. 0.5x? Oops, I said 0.5, you loser. Ooh, close. Oh, too much. Too much. Nope. Oh, it's close, but look, our green guy's above him, right? So we had to figure that out in a minute. That's fine. It's no big deal. We got this. We got this. Now, the question then, of course, is, well, I need a function that's always greater than it. And if you look at that, this thing's doing this number all the way down, and then you're like, oh, look. And then it does, what did I say? And then da-da-da-da. And they cross each other right here. And then the one line just follows it down. You're like, yeah, that's not above it. It needs to be above it all the way like so. You with me? It needs to be above it. Does it have to touch it? And the answer is no. Well, what do you mean? Well, for instance, hypothetically, what if I did this fella? Absolute value x. Is that greater than or equal to this guy all the way up? And the answer is, yeah, it sure is. Now, do they touch? No, it's not greater than or equal to. You see that? Oh, no, that won't work, friend. Are you with me? But what if I put a 1.1 in front of it? We Gucci now? Hey, we're Gucci now. Did it affect our limit at 0? And the answer is no, it didn't. Oh, friends. Oh, friends. Oh, friends. And so we literally, you're all clustered up because you're like, wait, all I gotta do is find it. Yes. And so the limit as x approaches 0 of negative 1.1x, absolute value x, is less than or equal to the limit as x approaches 0 of the tan of x times the cosine of the sine of 1 over x, which is less than or equal to the limit as x approaches 0 of the 1.1 absolute value x. And of course, since this limit is 0, therefore this limit must also be 0. Okay? Give me another one. A hard one this time. I guess. Okay, cool, whatever. How about this one? What? We just did this one. We know it's 1. Oh, I know. But check this out. Hey. Oh, doggy. Ooh, doggy. Now watch this one, friends. Sine x. Nope. Try again. Cos x. Oh, boy. Now listen. Is that going to work? On an open interval from negative pi to pi, you with me? Is the black always less than or equal to the purple? And the answer is 100% absolutely it is. Groom, what could I put on top of there? Well, let me help you out. You could do it this way. Oh, you whore. X squared plus 1. That would work, am I right? Is the red always above the purple? Sure is. What if I did this instead? Whoops. Oops, I lied. Bam! There you go. That would also work, wouldn't it? So what am I going to do? Well, I'm just going to pick one of them because I don't really care. And so I'm going to take the limit of the cosine of x as x approaches 0. And, of course, that's less than or equal to the limit as x approaches 0. By the way, Groom, how'd you do that back in the old days? Let me tell you, friends, it was hard because we didn't see the graphs back in the old day. Back in my day, by God, we couldn't see the graphs. Oops, I'm sorry, equals 1. And so we were out of luck, right? We had to kind of guess and check and feel about it and kind of, I think I'm right. What if my graph actually dipped below the other one? Well, what have I done? Well, I violated the rule, the theorem, and if I violate the theorem, is my conclusion right? Not necessarily, okay? So it was hard, but now you can look at the graph and you're like, freaking, it's 1. I can see it's 1. Cool, then all you have to do with the squeeze theorem then is show, and then in fact, that's true. Now, the reason I still bring this one up is I never do, I rarely, I shouldn't say never, I rarely do squeeze theorem to prove a limit. But what I do it for is I do it for the limit as x approaches 0. What I use it for is well, you'll see it in a proof sometimes, and you're reading some book, and they're like, well, according to the squeeze theorem, and you're like, Groom, did you teach us the squeeze theorem? So I tell it to you so that I can say I did, in fact, teach it to you, and I'm not a horrible teacher. Yay, there it is. So the limit is 1. And you're like, well, what would work there? What would work here? And yeah, you start dorking around with it, or you could just give it one of these numbers, negative x squared. Is that going to work? Sure, it's not going to work. Can I make it if it was steeper? Nope. And you're like, Groom, is that going to work? And the answer is, no, it's still not going to work, is it? So x squared ain't going to cut it. What about our abs? What about our buddy x? What about our buddy x, absolute value x? Oh yeah, up. He sure is, isn't he? Whee! Right on. So if you weren't certain about that, like, what could I do, Groom? All right, well, what could you do? What could you do? Black velvet equals, let's just say it equals x just for a good time, shall we? Well, that would be x squared is equal to 1 minus cosine x. Is that true? Is that going to work? Oops, does that ever work? X squared. Oh, you filthy hippie. Oh, too much stuff. Too much going on. Hey, look at that. They're never touched, right? So what does that mean? It means that our guy is always greater than the other guy, right? Yay, and then negative absolute value of x also, in fact, works. Again, a lot of times we're going to use him because he's a very handy fella to use. So all I got to do is, once again, take the limit. Hey, the limit of the absolute value of x as x approaches 0 is equal to the limit as x approaches 0 of negative absolute value of x, which of course is 0. So therefore, all I have to do is set it up. We know this guy is always between the other two functions, so I just got to set it up in the proper format, and huzzah, we have in fact proved it. Ta-da! I give you, friends, the squeeze theorem. Oh, for God's sakes. You want to do one more? All right, we'll do one more. It'll be a good time. I'm going to die. Oh, well, going out, doing what I love. Teaching mathematics. Yeah, right. Okay. The sine of t, or the sine of x, rather, sorry, times the tangent, the arctangent, that's disgusting, of the ln of x. Oh, gross. So here it is. Wee. What did I say it was? The sine of x. Sine x. Arctan of, what did I say? Arctan of the ln of x. Oh, gross. Now, where's there going to be a problem? Well, at 0, there's a problem. At 0, there's a problem. Well, what's the problem? Well, number 1, it stops there. Number 2, the ln of 0 is problematic, right? But it's going to be a one-sided limit. Can you see why? Because we're coming only at it from the right. Now, a guy says, listen, Groom, I feel like, and this is just, I'm just going to pull this out of my fanny here. I feel like you could make yourself a parabola x, actually, let's do this, parentheses x minus 0.5 squared, oh yeah, minus 2 minus a quarter, right? Minus, you're like, okay, Groom, I see what you're trying to do, but you didn't go down far enough. You're right, I didn't, did I? All right, now, what? Sam Hill. Oh, hang on. Oh, friend. Is the blue always less than the red? Oh, it most certainly is. OMG, Osh. And could I do something very similar with the top? I certainly could. For instance, let's just say I said x minus 0.5 squared minus a quarter. And you're like, listen, is the green always above the red in that same region? Let's say from 0 to 0.5. It sure is. And do they have the same limit at 0? Sure is. 0 minus 0.5 is 0.5 squared is 0.25 times 2 is 0.5. 0.5 minus 0.5 is 0. And the bottom one is a quarter minus a quarter. Ergo, the limit as x approaches 0 from the right of 2x minus 0.5 squared plus or minus 0.5. Now, by the way, this one is a bear if you don't have a graph. There's nowhere to know where to start on this thing. None. None. Welcome to my world back in the day. It sucked. Why did you go into math? Because I'm a loser? I don't know. I don't know. It's for the children, Mr. Groom. And so the answer is a goose egg. Okay, that's the squeeze theorem, the long and the short of it. Piece of cake. Have fun.